AP Cactus AB, Unit 6, Day 12, Office Hours, Multiple Choice Worksheet. You should have just done 1 through 15 multiple choice, leave the related rates on the back for our feature assignment. These are the answers to the multiple choice problems up here. I believe I posted them also. So pause the video if you need to check those, and we're going to go over them. Okay, assuming you checked them, let's see. So some of this is some, log and exponential derivative practice. So we got to do a product rule here. So f prime of x equals 3x times derivative of natural log of x is 1 over x plus natural log of x times derivative of 3x is 3. We'll try and clean it up. It's 3 plus 3 natural log of 3. 3 plus now, do we see that? Okay, there should be an x, sorry. 3 plus 3 natural log of x. So I don't see that answer. So we got to consider that maybe we need to use some log rules to combine it or multiply. So we can bring that 3 in as an exponent. And there it is. So sometimes multiple choice is more work. Problem 2, we're trying to find the derivative. So it's another product rule. So x times derivative, there's a chain rule here, 2 times the natural log of x to the first power. We can't move that 2 out in front. It's not on the inside. Chain rule times derivative of what's inside plus natural log of x squared times derivative of x is 1. So let's see if we can clean this up. The x's cancel, so we have 2 natural log of x plus natural log of x squared. And I don't see that answer, but I see a lot of answers that look factors. So I think I could take a natural log of x out of both of these, right? And this is what you would have. So there we go. Number 3. We got to take derivative and evaluate e, but you got to do the derivative first. So e to the x times derivative of natural log of x is 1 over x plus natural log of x times derivative of e to the x is e to the x. So if we're going to plug e in, we're going to get e to the e over e plus natural log of e times e to the e. Now natural log of e is 1. Rules of exponents say we combine these together by subtracting their exponents. So that's what I have, and I see that. Answer A. Okay. Number 4, I'm going to take a derivative. This is an exponential, not base e, so they are then their own. But then you got to multiply by natural log of the base. That's one extra thing. And then we got to do chain rule 3x squared. So 3x squared, 5 to the x cubed minus 2, natural log of 5, something like that. Do we see that? I think 3x squared looks like answer B. So, all these are based off of little mistakes. If you forgot the natural log of 5, which would be super easy to do, this would be your answer, right? They forgot the natural log of 5, and they forgot to do the chain rule. Right? So all these are based off common mistakes. Number 5, we're going to take the derivative and evaluate at 0. So let's start with the derivative. I'm going to treat that as a power function. So it's going 1/2 in front, e to the 2x plus 1 to the negative 1/2. Then we got to multiply by the derivative of what's inside, which is e to the 2x, and it has its own chain rule. Lots of little steps. You got to make sure you don't forget any. Now the 2's cancel, and so we get e to the 2x over the square root of e to the 2x plus 1. Oh, and then we're going to plug 0 into it. That's why none of the answers look like it. So it's going to be e to the 0 over the square root of e to the 0 plus 1. E to the 0 is 1. So it's going to be 1 over the square root of 2, which would be fine. Or we could rationalize the denominator, root 2 over 2. So Okay, moving on. So let's see, number 6, we're finding the second derivative. So you got to find the first derivative, which is going to be 1 over what's inside. Don't forget the chain rule. Multiply by the derivative of what's inside. So that's the first derivative, which is an answer on there, of course, with people not paying attention, not really looking at the second derivative. So the second derivative, we could do quotient rule, or you could do this, which would probably be a lot simpler. So you could do quotient rule, should work out. But this one would be negative 3x plus 5 to the negative 2 times derivative of what's inside. And that would be negative 9 over 3x plus 5 squared. So that's a little easier, I think, than quotient rule, but you should get the same answer. Number 7 we're trying to find the nth derivative. So probably looking for some kind of pattern. And we should probably start. So I consider this the 0th derivative. And then the first derivative, you got to do product rule. X times derivative e to the x is e to the x plus e to the x times derivative of x is 1. So first derivative, we get x e to the x plus e to the x. And the second derivative, we got to do another product here. X times derivative e to the x is e to the x plus e to the x times derivative of x is 1 plus the derivative e to the x is e to the x. So we get x e to the x plus 2e to the x. Third derivative, I think I'm starting to spot the rule. You gotta do another product here. X times derivative e to the x is e to the x plus e to the x times derivative of x is 1 plus 2e to the x is that derivative. And so we get x e to the x plus 3e to the x. You see the rule? I bet that the nth derivative is going to be x e to the x plus n times e to the x. That's my prediction, and now I got to make it fit one of these answers. So I think I could factor e to the x out. I have an x plus n. So I'm going with C. So establish a pattern. Look for a pattern. Number 8, I'm looking for an inflection point. So you got to get to the second derivative. First derivative is 2x. Derivative e to the negative x is e to the negative x times derivative of what's inside, negative 1, plus e to the negative x times derivative of 2x is 2. We could clean this up, if that helps. Okay, so then the second derivative is going to be negative 2x times derivative e to the x is negative e to the x times derivative of what's inside is negative 1 plus e to the negative x times derivative negative 2x is negative 2 plus 2e to the negative x times another negative 1. So if we clean this up, we have positive 2x e to the negative x. And here we have minus 2, another minus 2, minus 4 e to the negative x. So we're going to set this equals 0 and define, try and find potential inflection points. And we factor out a 2e to the negative x, with an x minus 2 left over. So that's never going to equal 0. X equals 2 is your inflection point. And I don't even think we need to do a line check, right? I mean, that's it. It's at x equals 2. I mean, the line check is just going to tell you where it's concave up or down. But if it had an even power on it, it'd be repeated even number of times, and it'd be a bounce issue, and then it wouldn't be an inflection point, even without a line check. So, number 9, we want to find the derivative at this xy point. This looks like a good implicit derivative, and we have an x and y value, so it should work out fine. Derivative e to the x is e to the x y times derivative of what's inside is product rule, better use parentheses. X times derivative of y is dy dx plus y times derivative of x is 1 equals derivative 2 is 0. Got to put these parentheses around it. So we could say, all right, well, x e to the xy dy dx. In fact, you know what we could do? We could just start plugging these numbers in right now. That'd be the smart thing to do. Because we have x is 1, y is natural log of 2, x is 1, y is natural log of 2. E the natural log of 2 is 2. So we have 2 dy dx is 2 natural log of 2 equals 0. 2 dy dx equals negative 2 natural log of 2 divided by 2. Dy dx equals negative natural log of 2. Negative natural log of 2. Or you could get the dy dx by itself and then plug the values in. But if you're going to plug numbers in, sometimes you do it sooner, later, it just makes the math a little easier. You're going to find the minimum. That's the absolute minimum. You don't have the endpoints, so we'll have to see. Maybe we can use a first derivative test or something. Got to find critical points no matter what. Take a derivative, set equals 0 undefined. So e to the x equals 2, natural log of both sides. So x equals natural log of 2. Now, that doesn't mean it's the answer. And plus, we need the y value. They put it right there, though, the x one. So, yeah, so we're going to do a line check. Natural log of 2 is definitely positive. If you think of the exponential graph, this is 1, 0. Natural log of 1 is 0. Natural log of 2 is somewhere over here. It's positive, so we could test 0 over here. And that's going to be negative, positive. So it's decreasing, increasing. And this is a relative min. But because it goes up forever on both sides, this is the absolute min. So it's going to be at this x value, but we need the y value. So we've got to plug that back into the original function. That's going to be 2. So we're going to get 2 minus 2 natural log of 2, which is the same thing as this. You could factor it out. Same thing. So we were able to pull it off without extreme value theorem. Justifying on unfair response would be a pain, but whatever. Works for now. Okay, 11. Which of the following functions grows faster than e to the x as exponential? Now, exponentials are known for growing very fast. You definitely beat polynomials. And, I mean, you can even sketch it. Quartic, I don't know, looks like this, but exponential is even steeper. A log looks like that. It grows, but definitely slower. E to the negative x is the same thing as 1 over e to the x. That actually is a decay function, so that's not going faster. 3 does, because this is 2.71 to the x. If you put a bigger base into an exponential, it's going to grow faster. And this one's going to be half as good, so it's got to be D. Do you know your graphs? Bigger the base, faster it grows. 12, your piecewise function it says it's differentiable, which also means it's got to be continuous, right? Differentiable requires continuity. So continuous would be if we plug 0 in, we get 3, and we get b. So these should be equal to each other if it's continuous. The two pieces got to meet. So we already got b equals 3. That's just from continuity. So then we should take the derivative, find the derivative piecewise. So it's going to be negative e to the negative x, and then a. Then we plug 0 into that. That's going to be negative 1. A is just going to be a, so a is going to equal negative 1. So a plus b is going to equal negative 1 plus 3 is going to equal 2. There you go. Quick way. 13, you have another piece y, says which of the following statements is true, which means it's got to always be true. F is continuous for all values. Well, we could check just like we did. Is it continuous? Let's plug in the points. These graphs on their own, I think, are fine. This is just an exponential shifted up and to the right, and this is exponential or decay. But the concern is at 5. Do they connect at 5? And they are the same, so it is continuous. So I'd say yes, it's continuous. F prime's derivative is continuous for all values, meaning the derivative is all connected. So we got to find the derivative first. Negative e to the negative x and e to the x minus 10. And so then we can plug 5 in there and see if those two pieces are connected. And they are not. These are not equal. So that's not true. The graph is concave upwards for all values. Okay, I don't know if we can say that's true. If the derivative is undefined at 5, then the continuity can't be defined at 5. So I don't even think we need to even look at it because it's not differentiable at x equals 5. So it's not twice differentiable at x equals 5, which means there's no defined concavity at 5, which is the middle of the interval. So we wouldn't say it's up or down at 5. Maybe it's upwards for everything else, but I don't even want to look at it because I know it's not going to happen for all the values. 14, let's see, the derivative is given. So they're giving the derivative 0 to 5 for what values of x at absolute minimum, and you're allowed to use your calculator. So I mean, trying to find the zeros, probably use a graphing calculator to do that. Or we could just graph the derivative. I think we could probably figure it out from that. I'm going to just type this in and see what happens. E to the x, parentheses, negative x to the third, plus 3x, close, minus 3, window, 0 to 5. Let's just graph that. So this is the derivative and just dives down here. I think we could probably figure it out pretty quick from this. So this is the derivative. So here, f prime is negative, it's decreasing, and then f prime is positive, it's increasing, and here f prime is negative, it's decreasing. Remember, the area in here tells you how much goes up or down. So we're looking for the absolute minimum. So it goes down, it starts over here on the edge, goes down a bit, goes up more. So this is probably the absolute min, the absolute max, and then it dives down. So the absolute min is going to definitely be over here on this edge endpoint. So at what value of x do you have the absolute min? 5. I'm not looking for the actual, I don't have to justify it. I mean, we could go in a lot more detail, but that's the quick way of doing it. You could find the area of each of these, but this area over here is so much bigger than all these areas. And that area is how much it's gone down. That's for sure the lowest point. That's the highest point right there. 15, we're going to take the derivative of this. So it's going to be itself, but then you got to multiply by the derivative of what's inside. So it's going to be 3 over x. So now 3e to the 3 natural log of x over x. Now I don't see that answer on here. So I should maybe think about trying to use some log rules. Now what I could do is I could bring this 3 inside, right? And then I know that e and natural log cancel each other out. So this is actually 3x cubed over x. I can use rules of exponents to say this is 3x squared. So actually my answer ends up becoming 3x squared if I know my log rules and I change it. So sometimes on multiple choice you just gotta be able to, change things up. Last page we'll do on a future date. So related rates, we'll save that for another assignment coming up. So